Okay, so we saw last time that rather than working with matrix equations to solve this eigenvector problem for our Hamiltonian, because we're dealing with the position basis and it's an infinite continuous kind of basis, this equation becomes a differential equation rather than a matrix equation. And so H will be some differential operator acting on our eigenfunctions, and if we solve that differential equation, that will tell us what our eigenfunctions are. And again, it's usually an infinite dimensional basis, so I'll have an infinite number of energy eigenfunctions, but they're countably infinite, so I can label them by some index n, where n can be just integers. And obviously, each eigenvector, each eigenstate will have an eigenvalue, En, going along with it. So how do we actually do this? Well, we need an expression for our Hamiltonian, and that's not tremendously difficult to do. We know the classical Hamiltonian is just the kinetic energy plus the potential energy, and so p squared over 2m plus v, the potential energy will be some function of x. And p and x are both observable quantities, so there should be operators corresponding to both of those things. So we just assume that our quantum Hamiltonian should just be exactly the same kind of thing, only they're operators rather than just variables. So we have our eigenfunctions here represented, or our eigenstates represented as in the position basis. And so we need our Hamiltonian also represented in the position basis if we're going to actually work with this. And I'll just, one day I'll go back and prove all of these things that I'm just saying. But for now, let's just take for granted that we know that the representation of our x operator is easy. It just becomes x in the x basis. And our momentum operator will become minus I h bar d dx. And so our Hamiltonian will become this. It's represented in the x basis by this. And so this eigenvalue equation becomes this equation. And obviously, depending on the potential, this will become a different problem. So I'll just, solve all of the usual problems that you would solve, work through some examples that you would see in a normal quantum mechanics course. But again, conceptually, we're doing the same thing we did before. We want to find the eigenfunctions, in this case, the eigenvectors, because once we've done that, we can just write down our state as in, normally when we're working in the position basis, we can write down the wave function as some linear combination of those states, and the Schrodinger equation is simple to solve at that point.